Alright, hello and welcome to our video. I'm Carlos from Plexus Lectures. Today we're just going over the Physics Paper 2 for the 2021 year. We've got the previous papers and in the future we should have some additional papers up, not just for physics. As well, if you're looking for additional resources like flashcards, some other learning videos, and some more MCQ kind of practice, hop onto our website at plexuslectures.com. All right, so let's jump into question one. So question one, a charge of 2.8 times 10 to the negative 7 coulombs experiences an electrostatic force. I'm just going to zoom in a little bit. Electrostatic force of 5.2 times 10 to the negative 1 newtons when placed near a charge of 3.2 times 10 to the negative 7. Calculate the distance between the two charges. So it's important to do, so I've probably talked about it a fair few times in our previous videos, is read over the question if you're uncertain about what the question is or where to start. First think about what topic it falls under and the topics that you've learned in your physics curriculum. Here I'm thinking about electromagnetic fields and some of that kind of force content as well. The next thing is I'm going to look at my formula book. I'm going to go through my formula book and have a look at what kind of variables they've given me in the question. Like this, the charge. I've got two charges and I've been also given a force. Now some information can be a red herring. In the case of this question, it's not quite. So what I know is we have two charge points. There are two charged points. And there is a formula for the force between two charged points at a given distance. And that's going to be written as, in our formula book, it is F1 over 4 pi E naught. And this value here, we know that as Coulomb's constant, and that's also given to you in the back of your formula book, multiplied by capital Q, lowercase q, over r squared. So let's list out what variables we have here. So capital Q can be one of our charges. Whilst we read through the question, it's important to check as well that the units you've been given are correct. So we've been given a charge in 2.8 times 10 to the negative 7 coulombs, and that's correct. I don't need to change that. Our second charge is going to be this 3.2 down the bottom here. So 3.2 times 10 to the negative 7, and that's in coulombs as well. And then finally, our force, N, is equal to 5.2 times 10 to the negative 1 newtons. So fantastic. Again, that's in the correct units. And for sanity's sake, I'm going to write out coulombs. I'm going to let it be K. Actually, coulombs spelled with a C, so I'm going to use it as C. So let's not get confused with our other C's for our values. So coulombs is 9 times 10 to the power of 9. Now that's in the back of your formula book. I don't remember the units off the top of my head, but what we can do and what you can think about is if you were to multiply through, your units should cancel out when you rearrange it to figure out the units. In our case, we're trying to find the radius, and radius is measured in meters. So another tip that I've probably talked about a fair bit in previous questions is I always like to rearrange my equation first before I substitute any variables in. The reason for that is it can be a little bit cumbersome if you have multiple variables already written in and you have to keep on rewriting out such a large number. So thinking about how we rearrange it, so I want to move the C over to the other side, so it's going to be F divided by C is equal to Q over r squared. So I'm making sure I'm not forgetting any variables as I go through. What I'm going to do here is an inverse. So what ends up happening is I have Q lowercase q K divided by F. So what I've done is essentially this is now Q lowercase q divided by F over, that should be a C, sorry for our coulombs, F over C. And I've just inversed this here and it multiplies it. And it can rearrange to our below statement. It is equal to r squared. Final step is r is going to be equal to the square root of q multiplied by Coulomb's constant divided by the force. And now this is where I can put my values in. So the square root of, I have 2.8 times 10 to the negative 7 multiplied by 3.2 times 10 to the negative 7 multiplied now by our Coulomb's constant, 9 times 10 to the 9, all divided by our force, which was 5.2 times 10 to the negative 1. And you see how now when I substitute my values in, or my variables in, it ends up being such a large task to write that all through. Now, some students might simplify it beforehand. It comes down to what works best for you. So what we end up getting is 0.03328 meters. Remember, our units is going to be in meters. And what do we want? 2 sig figs, so that's going to be 0.033. And so that's question 1. So let's continue on. All right, so question 2, list the 4 types of gauge bosons in the standard model. Now, I'm not going to go over this one too much. It is a listing activity, so you can have a gluon, a photon, as well as a W boson and a Z boson. Now, what I do recommend is for those students that are having difficulty remembering this, definitely hop on over to our websites in the description of the video. And we've got flashcards as well as we have learning videos for the content if you haven't understood it yet. So definitely jump over there and use our resources, which will make hopefully a big difference for you guys. Okay, so question 3. An object undergoes uniform circular motion in a path with a radius of r. I'm going to highlight as we go through. Determine the effect of the radius if the mass of the object is doubled, but the centripetal force and the velocity remain unchanged. So this is a relationship or a formula relationship question, very similar to one of the MCQ questions in the paper 1 for the 2021 paper, where you had a formula and you've got to determine what's the relationship if you change one variable and you keep all but one other variable constant. So in this case, let's think about the formula we're using in this relationship. This is going to be, think about what topic it falls under. This is our gravity and motion. Have a look for a formula with all the right variables or the same variables that are mentioned in this question. So F is equal to mv squared over r. So these are the variables that we've mentioned. And what we know is some variables are going to be constant. So we're going to kind of use, a simultaneous approach, and that both forces, the centripetal force in our centripetal force calculation is constant. We're going to have 2 variables. Our mass in one equation can be capital M, and our mass in the other is going to be 2m. So m is going to be equal to 2m. The reason for that is because in the question it's told us the mass of the object is doubled. Now, the other variables, v is constant, so v equals v in both situations. It is constant. That's one thing to remember. So in all our equations, v is constant. The radius, on the other hand, is going to be r in the first one, so I'll call it like r1, and r in the second one can be capital R, so we don't get it confused. So I'll write the situations out and we'll have a little look at what we're talking about. So remember, both situations, the force stays the same. So I'm going to set the equation as capital M v squared over lowercase r1 squared, no, that's not squared, equals to 2 capital M. That's where we've subbed it in where that M is there. So I'll get rid of those brackets. V squared again. V in both of these equations are the same because V is constant. How do we know V is constant? Velocity, it remains unchanged. Over capital R this time. Remember, our radius is the thing that changes, but we want to know by what factor. If we double our mass, what ends up happening to our radius? Now, some students might already be able to look at the question and already realize what happens. If you double the radius, if you double the mass, you've got to do something to the radius for the 2 equations to equal the same. So what we're going to do, for the 2 equations to solve. So what I'm going to do is run through and cancel out some variables. So I want to get rid of that mv squared. So how do I do that? Is going to be, I'm going to divide the left-hand side by mv squared. So r1, and then divide it by mv squared is equal to capital R on 2. And what do you know? That cancels that out. That cancels that out. So my next step is going to be 1 on R1 because it's cancelled out on the top of our fraction is equal to 2 on capital R2. What we can do is inverse both solutions. So that would just be R1 divided by 1 is R1 still. And here we have R2 over 2. And then what we can do is we want to know what the relationship is with the original radius. So capital R is going to then be equal to 2R. So if you double the mass, so therefore, if the mass is doubled, the radius must be doubled, and I would continue if all other variables remain constant, such as the centripetal force. So happy with that one? We'll continue on. All right, so question 4. Again, I'm going to highlight as we go through. A spacecraft is located between two large asteroids, asteroid A and asteroid B, that are 120 kilometers apart. Asteroid A's mass is approximately 4 times the mass of asteroid B. So again, we're kind of getting into a similar scenario as the previous question. Determine the distance between the spacecraft from asteroid B if it experiences no net gravitational force from the two asteroids. Now what I'm going to do is take our time and we're going to draw the scenario out, or the situation out. So we have two asteroids. We have asteroid A sitting here, and we also have asteroid B over here. What we know is they are a distance of 120 kilometers apart. Now, in between these two asteroids, we have, it's a horrible straight dotted line, but in between is our spacecraft. I'm going to denote it with an X. Now, I'm going to throw some other terms in there so we can think about what's happening. Our spacecraft is going to be a radius of RA from asteroid A, but it's also going to be a radius or distance from B of RB. So I want you already thinking about that we can put the terms RB in terms of RA or RA in terms of RB, because RA, so a quick thing to note, I'll erase it and we'll come back to it. RA plus RB is going to be equal to that total distance. It's this distance here tacked on to that distance there, and that's going to make our 120. So that's going to be an important thing to remember when we come back to it a little bit later. So I'll cross that out for now. So another thing to note is the mass of our two planets. So I'm going to say MA is going to be equal to something, and MB is going to be equal to something. So what we know from the question is asteroid A is mass is 4 times that of asteroid B. So I'm going to say asteroid B, or MB, the mass is just going to be equal to M. And MA is 4 times MB, which is 4 times capital MB, which would be equal to 4M. So I'm just going to get rid of that fluff and we'll just leave it as 4M. All right. So now we've kind of cleared out what's happening. One other final thing to think about in this question is it's talked about determine the distance between the two asteroids, or from asteroid B, if it experiences no net gravitational force from the two asteroids. So what does that mean? That means the force, the F gravitational G of B is the same as what the force F gravitational of A on that spacecraft is in both directions. So another way to write that as a statement would be, because we're just worried about the magnitude of these two, I'm just going to say force of gravitational due to planet A or asteroid A magnitude is equal to Fg of planet or asteroid B. So these two statements are equal to one another. So I'm just using the absolute values because they're pointing, or force is a directional vector. They're pointing in opposite directions, so one would be negative. I don't care about the negative, so that's why I'm using absolute values. I just want to know the absolute, the positive value, that they're both equal to. So my new statement now is I think about what's the formula for my Fg of a planet, or of a object sitting on a planet from a radius from its center. That is going to be Fg is equal to capital or lowercase m to start off with, capital M, the mass of your planet, or in our case, our asteroid, multiplied by G, divided by R squared. So let's write this new statement now. We have FGA is going to be equal to I'm going to say lowercase m is the mass of our spaceship. That's going to just be ms. And because I don't want too many capital or lowercase, I'm just going to have capital M for these two here. So that's that fixed up. So now, our situation, we've said the two forces are going to be equal to one another. So lowercase m s, I'm going to put the g out the front because g is our gravitational constant. ms multiplied by m mass of object. So this is going to be for asteroid B, or no, sorry, I'll keep it for asteroid A on the left-hand side, multiplied by 4 capital M divided by r squared. And we'll get back to what these r squared values are, but this is going to be the r squared for planet A, and that's going to be equal to g ms, the mass of our spaceship, multiplied by capital M this time, because it's the mass of planet B, divided by radius B squared. So now I'm going to continue rearranging through, simplify some things, so I know I can cancel out my g's. That can cancel out. Same with my mass of my two spaceships, that can cancel out, and the same goes for my capital M. The 4 is going to stay because the 4 is the magnitude of, or the magnitude difference of asteroid A compared to asteroid B. So my new statement is going to look like 4 over RA squared is equal to 1 over RB squared, if that makes sense. So what I'm going to do from this point now is inverse the 2, same as what we did with the previous question. So that's going to be RA squared over 4 is equal to RB squared, don't forget the square, and then I'm going to multiply by that 4. So moving that 4 to the other side, I get RA squared is equal to 4RB. And then what I'm going to do is I want to get rid of the square on each side, so I'm going to square root. So square root of that complete side. Remember, when you do the square root, you're doing not just the square root, so that should be a square in there, sorry. Not just the square root of the r squared, but you're also doing the square root of the 4. What that's going to give me is radius A is equal to 2 radius B. So in this case, we said it before, 120 is equal to RA plus RB. So in this case, I'm going to figure out what RB is. So RB is equal to 120 minus RA. So I'm going to substitute that now down in that question or that step. So RA is equal to 2 times 120 minus RA. What I end up getting, RA 240 minus 2RA. I end up getting 3RA over here because I'm moving that is equal to 240. Therefore, RA is equal to 240 over 3. So 240 divided by 3 is 80. And so remember, our question was distance from asteroid B. So distance from asteroid B, we're going to substitute our RA value back in up here because that's going to get our RB. So RB is equal to 120 minus our RA value, 80. RB is equal to 40. Now remember, the units we were working with here, we were working with kilometers for our R's, so it is going to be 40 kilometers. So this is definitely worthwhile a question to go back through. Some steps can be done differently depending on how you want to work out the solution. So it's definitely worthwhile. A good tip is draw out the situation or draw out the problem, seeing what's happening. What does it mean when the two forces, or there is a no net gravitational force from the asteroids? Visualize and try and think what that looks like. And then again, with the majority of these, it's thinking about simultaneous equations, or one of these variables is constant between the two or is equal. So very similar to the previous question we did over here. All right, question 5. An alpha particle with a charge of positive 3.2 times 10 to the coulombs moves through an electric field accelerating from rest through a potential difference of 240 volts. Determine the velocity of the particle at the end of its acceleration. expressing your answer in scientific notation. So we'll leave the scientific notation for the last step. But the thing that we want to think about now is how are we going to be able to determine our velocity of the particle given we only know the charge and the voltage it's traveling through. So an important thing to recall upon is that a charged particle moving through an electric field completes work, or we can have our potential energy or think about it like that. And from our potential energy, our PE, we can also figure out our KE, or sorry, other way around, our EK, our kinetic energy. So the thing that we want to realize is, I'll write it as a note at the top of this, a charged particle, I'll try to write it quick and abridged, a charged particle moving / accelerating through an electric field. Completes work. And that's equivalent to our statement above. So that line there, our potential energy is equal to our EK. So what do we know? How can we calculate the potential energy? You'd know from some of the year 11 content when you were working through circuits that the formula we're looking at is voltage is equal to the change in work, so U over Q, so the charged particle. So what we can then rearrange that to is delta U, or in this case, it's going to be, instead of delta U, I'm going to call it PE, is equal to V voltage multiplied by our charge of our particle. So an important thing to remember is your work or your potential energy or potential energy and kinetic energy, they're all measured in joules. So depending if the question has given you a statement in different units, it's important to think about. But in this case, we are just working for our potential energy. So that is going to be our voltage that we've underlined at the top, 240, multiplied by our positive charge of 3.2 times 10 to the negative 19 coulombs. So we end up getting 7.68 times 10 to the negative 17 joules. And so as we said before in this top statement, I'll now circle in green, is that we have potential energy is equal to our EK. So our EK here, if we write kinetic energy, is going to be equal to 1/2 mv squared. Again, I'm going to probably be repeating myself multiple times. I always like to rearrange my equations first before I substitute in any values. It's going to save me a lot of writing. So we're rearranging our EK because our EK is equal to that there, our 7.68 times 10 to the negative 17 joules. We're going to have the mass of a alpha particle that's in your formula book. So you get masses of other particles as well. So usually should be a trigger. If you see the mass, it's not given to you, you should be able to find it somewhere in your formula book. So our mass is going to be equal to 6.64 times 10 to the negative 27, and that's in your formula book. All right, so what we're going to do now is rearrange our EK equation. It's going to be 2E, I'm going to drop the K, mv squared. V squared is equal to 2E divided by m, and then V is going to be equal to the square root of 2E divided by m. And that's going to be equal to the square root of our 2 times our charge. Move those brackets. So 2 times our charge, which is 7.68 times 10 to the negative 17, all divided by our mass of the charge, the mass of our alpha particle, 6.64 times 10 to the 27. And that is going to be equal to, I'll do it in the next line underneath, 152,093.82 meters per second. So remember your units, what we're working with here. We made sure we had coulombs was our base unit here, as well as joules was our unit here. It wasn't kilojoules, because if we had kilojoules and then substitute it into that equation, we're not going to be working in meters per second. So we need to make sure our base units are the SI units as we work through to get to our solution. So what we can do is to get that to significant figures, two significant figures, that is 1.5 times 10 to the 5, and they already have our meters per second at the bottom there. So an important thing to flag with this kind of question is that it has a little bit of like stepwise progression, and you have to kind of realize what's happening in the scenario. If you're going into an exam without any practice at all or any prior revision, you're not going to be exposed to any of these kind of problems where it's stepwise, you have to think or link between some of your content. So it's worthwhile always doing that revision, so you get more exposure. And then the way that I like to think of it is those complex unfamiliar, they may still be complex, but hopefully they become familiar and you'll be able to stepwise and think through it. Oh, I've seen something similar like this before. Okay, so question 6, starting from the top. So the diagram below shows a magnetic field lines inside a solenoid carrying a current of 2A. So here we have our solenoid with the current going in the direction of my pen. And what our first question is, calculate the number of turns per meter that would produce a magnetic field strength of 300 UT. So what we've got to first think about is, in this situation, what formula or what kind of information have we been given? What are we trying to calculate? So we're trying to calculate the number of turns. We already know this is going to fit under our magnetic fields kind of content that you've learned. And so I'm looking through my formula book. I'm looking for, okay, I have magnetic field here. That's going to be B. I'm looking for, I have given up here the current. So that's I. I've also been given, or not being given, more or less asked for the number of turns. So number of turns is N. And so the formula I usually look for, or the formula that's going to call out to me, is going to be B is equal to U naught N I. And so that's our formula we're going to use, but we're going to rearrange it because we are trying to calculate N, the number of turns. So I'm going to quickly rearrange this. So next step would be B divided by U naught I. And so that is going to be equal to N. So N is equal to B over U naught I. Now, before we substitute anything in, it's important to realize we have UT. So what we've got there is microteslas. So what we need to do is convert that units to teslas, because otherwise we're not going to get a correct number of terms or turns for our answer. So I'm going to look in my formula book. It's important to not rely on your formula book for your conversion of units. You should be fairly familiar with it beforehand. But in my formula book, I am just going to look for what is it to the power of, and then multiply that unit to get it back to standard teslas. So we have B is equal to 300 microteslas. And then what I want to do is to convert that to teslas. I'm going to multiply 300 by 10 to the negative 6. That's going to get me my teslas there. And so if you ever get stuck in an exam, you can't remember how to convert, there's two ways. You can either multiply it or divide by. And so, or you can always multiply, and you can think about, is it going to be a negative to the 6 or a positive? So if it's a negative to the 6, I'm expecting this to be a very small number because it's microteslas. If it turns out, if I put a positive number, I end up getting 300 times 10 to the 6, and that's not going to be the same as that. That's like so much more magnetic field strength than the original. So that's where I realize, okay, maybe it's to the negative. So you've got to think of ways to, I guess, get to a solution if you don't remember the exact process, or a way to rationalize, okay, is my actual answer I've gotten here actually a reasonable solution? And to me, it's like, yeah, it is. I have it to the negative 6. That makes sense. There's a lot more zeros sitting in front of that 300. All right, so continuing on, we're just at the stage of just substituting in now. So N, or number of turns, is going to be equal to B, which we've now decided is 300 times 10 to the negative 6, all over U naught, which is 4 pi times 10 to the negative 7, multiplied by 2, which is the charge, and it's 2 amps. There's no micro or anything like that. That ends up getting us 119 turns. All right, part B, determine the direction of the magnetic field produced by the solenoid. So this is where we're going to use our right hand, so horrible handwriting, right hand rule, and be prepared for a horrible drawing for my explanation. But what we need to know for our right hand rule is the direction of our current. We know the direction of our current is essentially going that way if we track it through the coils. Now I'm going to get rid of that for now. So our right hand rule is you use your right hand, place your palm underneath. So your palm would be underneath. Here's horrible pinky finger. I'll start again. Palm's underneath. You have one finger there, another finger, another finger, another finger, and then you have your thumb, which is sitting again underneath but pointing. It's not quite a thumb, pointing in the direction of the current. So our current, as we've said, I'll do in a different color, is going through like that. But if we just put a net direction of our current, it's like that. So from that information, I'll also add a little bit of a label palm here. So we know that's the palm of your right hand. So what we know is our magnetic field lines will pass through and loop around. So they'll go like this and loop around. And so that ends up being north, and that is our south there. So when we write the answer to our direction of our magnetic field lines, it is going to be from south to north, so left to right. All right, so question 7, we have a graph question here, and again, 2 parts, similar to question 6. So an object on a planet is launched horizontally from a cliff. Its vertical displacement is measured over 6 seconds. The graph shows the object's vertical displacement with respect to time squared. So this is going to be an important thing to remember. Any graph you're looking at, take note of what your y-axis units are in. It's in meters, and what your x-axis is. It's in seconds squared or time squared. So these are going to be important factors to think about when you go through an equation. And so before I read part A and part B, or read those questions within the set, I'm just going to quickly think about what's happening in this situation to help you guys along. So here we are on a cliff. There's an object and it is launched horizontally. And so what ends up happening over time is it gets down and down and down. Usually, I personally, when I write my questions or write my solutions, when I think about these problems, displacement I think is negative as it moves down or over time. It's getting further away, but they've denoted as it gets closer to the ground or as it moves further away from the origin, this downward direction is a positive displacement. That's not going to make too much of a difference. It's just an important thing to think as we work through the problem. All right. So determine the mathematical relationship between the vertical displacement and time. So they want specifically time, not time squared. So let's have a look at our graph. Firstly, I think it is going to be a linear relationship. So that's probably going to be an important thing I state in my solution. Linear relationship. And what do we know about a linear relationship? We can, I'm having a little bit difficulty writing it out. A linear relationship is y is equal to mx plus c. Plus c, we have a 0, 0, so crosses or position at time 0, or at time squared 0, the displacement is 0. You're at your starting position. So position 0, 0 is our original displacement. So we know c is equal to, therefore c is equal to 0. Another thing is our x is actually, or let's go through what our y is equal to first. Y is equal to sy, our vertical displacement. X, on the other hand, is equal to our time squared, so t squared. Now, on the other hand, m, which is our gradient always has a formula which is equal to our change in y over the change in x. And in this case, we're just going to pick 2 positions. I'm going to use the 0, 0 as one of my other positions. And then I'm just going to use this position at the top here, which is going to be 94 meters. at a time of 35, or at a x value of 35 seconds squared would be, oh sorry, it's 36 seconds squared. So to write it out, it is going to be 94 minus 0 over 36 minus 0 equals 2.6. So we end up getting a relationship of is SY, because I'm just substituting now all of these values back into that equation there, and not forgetting that C value over there. So that ends up being SY is equal to a gradient of 2.6 multiplied by our x value. Remember, x is equal to time squared plus a 0. I'm not going to write it out, and that's our relationship. So our vertical displacement here is going to be equal to 2.6 times time squared. All right. So part B is calculate the acceleration due to gravity on the planet. So what we're going to have here is there are two solutions, or two ways you can think about getting to the answer in this question. So what I'm going to do is, on the left hand side is going to be solution 1, and over here on the right hand side we will talk through solution 2. So solution 1 is going to be the expected route to go through for this question. So I'm going to write this as the topic, or the way that I would think about it. This is just using your linear motion equations. So others might have heard them as kinematic equations, but things to think about is our original gradient, or the mathematical relationship in part A. We figured that out as being SY is equal to 2.6 t squared. And think about, we're trying to calculate the acceleration. I'm going to look for a linear motion equation that has similar variables, and I can try and abridge and think about it. So the other linear motion equation there is SY, or just in general, its displacement, is equal to UT, which is the initial velocity, plus 1/2 AT squared. And so what we know in this situation is, if I scroll back up, we can think about it. The UT is going to be, or before I even go through it, is let's think about it. We want the acceleration. The acceleration is only present in the y. So this is going to be SY is equal to UYT plus 1/2 A. I'm going to neglect the y because acceleration is only working in the y, t squared. So the thing that we're going to look at is, I'll quickly go back to our solution, and we know it's launched horizontally. So our uy, or our initial y velocity, is equal to 0. So the next thing I can write out would be SY is equal to 0 times time plus 1/2 AT squared. Then we can look at it as SY is equal to 0 times time, or 0 times anything is going to be 0. We are left with 1/2 AT squared. That SY 1/2 AT squared looks awfully familiar to our original mathematical model or relationship we've discussed. So we have underneath SY is equal to 2.6 times, or 2.6 t squared. So that 2.6 lines up with our 1/2 AT. So I would write 1/2 A is equal to, sorry, I said 1/2 AT, but 1/2 A is equal to 2.6. Therefore, we just rearrange it. A is equal to 5.2. So I'm going to write that here, and it is 5.2 pointing downwards, so it's 5.2, and our units is meters per second. Now the other solution is for those who are doing methods or specialists and thinking about derivatives. So a derivatives solution makes us think about our relationship here to our SY is equal to mt squared. And so what we know is, if we do the derivative of displacement, we get the rate of change of displacement, which is actually our velocity. So dsy, d time, would be equal to velocity. And so if I do the derivative of this equation here, I end up getting Vy, our velocity, is equal to 2mt. And then what I end up doing is now if I do the derivative of our velocity equation in respect to time, so our dvy dt, that is going to be our acceleration. And then if we actually do the derivative, we end up getting acceleration is equal to 2 multiplied by m. What did we say our m was in the original statement? 2.6. So 2 times 2.6. And we also get 4.2. And again, it's meters per second squared because it's acceleration. And you can kind of rationalize it a little bit more better in this derivative approach why the units are meters per second, because you're doing it to the derivative in respect or regards to time for the second time through. And I just realized before we move on to question 8, I'll just quickly correct a mistake. I believe I said 4.2 here, and it should be 2 times 2.6 is 5.2. So if anyone was confused, that is 5.2, just like our solution there. All right, so question 8. Looks like we've got another graph question similar to question 7. So a photoelectric effect experiment was conducted by shining light from a laser at one frequency, so it's a constant frequency, at 5 different metals with known work functions. The graph shows the maximum kinetic energy of the photoelectrons ejected from each metal with respect to their work functions. So just to add a little bit more context to what they're talking about, there's 5 different metals. So that would be metal 1, metal 2, metal 3, and so forth. Now, an important thing to register with this is, again, think about what are your units on your y and your x axis. So on your y, we have kinetic energy, Ke, or sorry, keep on doing Ke, but Ek. And I'm going to highlight it because this is going to be a common mistake that people will make, is that they don't realize it is 10 to the negative 9 joules. And same with our work function down here. So our x-axis is our work function. And with that in mind, it's our work function for each independent metal. So let's continue through, and what we've been asked now is determine the wavelength of the light emitted by the laser. So I'm going to quickly write out what I know about this scenario. This is another linear relationship or linear model. And that can be modeled by y equals mx plus c. But what other formulas relate to this scenario? So the scenario here relates to our photoelectric effect function or formula. So it relates to this one here. Our Ek is equal to Hf minus W. And what I can think about, or what I can try and map up, is our y is equal to mx plus c. I might slightly rearrange this because in our case, x is equal to w, our work function over here, and y is equal to our ek. And so if I was to rewrite it, I'll do it in green now underneath. Our ek, which is our y, is equal to m multiplied by w plus c, which in this case, we can map it so it links to this formula here. Ek is equal to c, which is now hf. I can see that c here and c here is the same c here, is equal to minus, or I'm just going to leave it as plus because we'll work it out in a second, plus mw. So the thing that I want you to think about is, what is m here? We know we have a negative 1 m here, so let's prove what's going on in our situation. So we know we're on the right track. So our gradient m is the change in x over the change in y, and let's pick some values. So I'm just going to pick here m2 and our metal 5 essentially. So our values we end up getting from that is going to be 0.45 minus 1.45 over 7.6 minus 6.5. And I'm not going to put the times by 10 to the negative 19 in each of these values because it's dividing through, it will end up cancelling out. So what we end up getting for our m is a value of negative 0.91. Now that 91 is very close to our negative 1 gradient that we see here in our original photoelectric effect function. So I'm happy to assume that m is equal to negative 1. Now, the example they give in the worked solutions by the QCAA is, I find it a little bit unfair. They don't use these exact values in here to calculate the gradient. They draw a trend line and map out to a certain point and then calculate that negative 1. So I'm going to go with this fact here that our value is m is equal to negative 1. So we are left with a statement of HF is going to be equal to our C value for our linear model. So we need to figure out our C value, which is the point where it crosses our y-axis. So I'm going to continue over the page to continue my working. And I guess before I continue is I'm just going to again pick a point, because what I'm going to do is I have our relationship of y is equal to essentially, or I'm going to neglect the y from this point forward. Our EK is equal to our W, or HF minus W, or in this case C minus W. And so I'm going to sub in a point on our graph. So I'm going to sub in the 7.6. Now this is where it's important for our times 10 to the negative 19, because if we substitute back or think a couple steps down the line, our HF value, where H is Planck's constant, it's going to be very important, times 10 to the negative 19, and we have 0.45 times 10 to the negative 19 as well. So if I sub those values in, I have 0.45 times 10 to the negative 19. So I'm doing my cardinal sin of subbing in my values before rearranging, is equal to C minus our 7.6 times 10 to the negative 19. We rearrange that, we end up getting a C value is equal to 8.05 times 10 again to the negative 19. What is C equal to? C is equal to HF. And what is our F equal to? And so I'm just going to do our 2 dash. F is going to be equal to our 8.05 times 10 to the negative 19 divided by H, which is Planck's constant, otherwise 6.626 times 10 to the negative 34. And then what we end up getting is a frequency of 1.2149 times 10 to the 15. Now this is in our solution. Remember, we want wavelength as our answer. So what is frequency, or our wavelength formulas? We think frequency is equal to the speed of light over the wavelength. So therefore wavelength is going to be equal to speed of light divided by our frequency, which is equal to our 1.2149 times 10. Oh, other way around, sorry. Our speed of light is 3 times 10 to the 8. And our frequency, as we've already denoted up here, is 1.2149 times 10 to the 15. And that ends up getting us 0.000, another 3 zeros, 246, 24693 meters. Our answer is in nanometers. So what we end up doing to convert that to nanometers is going to times that by 10 to the negative 9, 10 to the positive 9 in this case, and we end up getting 247 nanometers, because we're rounding up to the nearest whole number here. And again, for when you're converting your meters to nanometers, think about that situation we talked about in the previous question. I think it was question 6 when we're converting our microteslas to teslas. So we're on the final question of the paper, question 9. So question 9, I'm going to just write very minimally here. The best, I guess, explanation or the best written solution is have a look on the QCAA website or have a look at the link in our description. We've got a link to our own annotated sample answer to this question. And so I guess the thing that we need to think about is explain how Young's double slit experiment or double slit experiment provides evidence for a wave model of light. So the three things that I want to do to explain for the wave model of light using Young's double slit experiment is first, let's describe what the experiment is. So the experiment from memory is going to be, so describe the experiment. So the experiment is there is a torch here at one point, there is a wall, and it has two slits for the double slit, and what ends up happening is light goes up to it and it gets to these points here, and light ends up going outwards at that point and branching or getting wider and wider, and same with light here. It gets wider, 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 and wider. And then you have a detection wall. And on that detection wall, you get different intensities of light. And so now we're on to the step of describing the results. So describe the results of the experiment. So the results were that you get different dark and light spots. And now that final spot is like, let's relate those results. What do those results mean, having light and dark spots? And that's because we end up getting similar to our wave or mechanical wave behavior is we get constructive and then we also get interference or destructive interference at different points. And so when it gets to the wall, we're going to have waves that are in sync versus waves that aren't, and so we're going to get brighter spots at some points and we're going to get darker spots at others. And so that's going to be the reasoning behind or how Young's double slit experiment provides evidence of the wave model of light, is because we can see here is that these waves, as they leave those slits, they overlap one another and they can cause constructive or destructive interference, and that's how we can explain it, similar to a mechanical wave behavior if you were to do the same thing on an ocean of water or on a body of water. All right, so that's going to conclude our walkthrough for the 2021 paper 1. Oh, sorry, paper 2. Thank you for watching.